Okay, welcome everyone. I'm delighted this afternoon to introduce our AI distinguished lecturer, Cynthia Dwork, who many of you know. Cynthia is one of the most accomplished technical women who I've ever been around. She has 4 fancy titles right now. She's the Gordon McKay Professor at Harvard in the Computer Science Department. She's also the Radcliffe Alumna Professor at the Radcliffe Institute for Advanced Studies, and she's an affiliate faculty at the Harvard Law School. In addition to that, she's a distinguished scientist at Microsoft Research. She was one of the inaugural class of distinguished scientists here about a decade or so ago, maybe a little bit more. Cynthia received her PhD at Cornell with John Hopcroft. From there, she did a couple-year postdoc with Nancy Lynch at MIT, and then went on to spend a fair amount of time at IBM Almaden, where she did a lot of foundational work that I was not all that familiar with until earlier today. The work I knew about that she did there was something on rank aggregation, which was very important in web search. She also did work on cryptography foundations, as well as proof of work, which is one of the underlying foundations of Bitcoin. At MSR, she is well known for 2 other strands of work. One is on differential privacy, putting privacy on theoretical firm ground, and it's incredibly important today. And what she'll talk about with us this afternoon is more nascent work on algorithmic fairness. This work and her lifelong accomplishments have been acknowledged by more prizes than I named, more prizes than the fancy titles I mentioned at the outset. She's obviously a fellow of the ACM. She won the Dijkstra Prize more than a decade ago. She won the Godel Prize. She's one of the very few people who are members of both the National Academy and National Academy of Engineering, National Academy of Science and National Academy of Engineering. She's an amazingly adept scientist, and one who picks problems that have real practical impact, which I think is a really unique skill. So with that introduction, I'd like to introduce Cynthia, who will tell us about some of her work on algorithmic fairness.
Thank you very much for that gracious introduction. Thank you for inviting me, Emre. I'm really very happy to be here. I have a couple of questions before I proceed with the talk. So first of all, how many people here are working in machine learning and AI? Okay. How many people here have worked on fairness particularly? All right. And any theoretical computer scientists? Great. All right. Good. That helps me figure out what I should be saying. All right, so this is a research effort that actually began at Microsoft's now defunct Silicon Valley lab. Started in approximately 2010. And I should mention that all of the good slides in the talk are due to my student, Cristina Ilvento. So here's our problem. We're interested in algorithmic fairness. We'll be more specific in a minute. We have a population. Our population is diverse in many different ways: ethnic diversity, religious diversity, geographic, medical, and so on. And, well, whatever it is we want to do, we want to be sure that somehow or other we're being fair. So typical examples would be something like this. We have a bank that receives detailed user information about you before giving you your online experience. So you surf on over to some bank, and before they show you anything, they consult with tracking networks and find out stuff about you. And the concern, and this was a concern that was raised in a newspaper article in the Wall Street Journal in a series that they ran in 2010 called What They Know. It was mostly about privacy, but it also raised the following fairness concern. The concern was that of the illegal practice of steering minorities to credit card offerings of less desirable terms. The financial industry is more heavily regulated than many other industries, and so this problem really was a legal one, not just, quote unquote, a fairness one. So just to dispense with some obvious things, one suggestion is, of course, to hide the sensitive information from the classifier. So whether you're a member of a minority group or not would be hidden. And that falls victim to a couple of things. First of all, there's redlining. Who knows the term redlining? Great. We'll see a picture of it in a minute. And on the web, there's weblining. And I'll get, so this is basically, say, when zip code is used as a redundant encoding of race. It's illegal to discriminate based on race. It's not illegal to discriminate based on zip code. So we have this issue now in general of redundant encoding. Sensitive attributes can be embedded holographically in your other attributes. And the other is this sort of birds of a feather phenomenon. So has anybody seen this picture before? This was an undergraduate research project at a class at MIT. This is not sort of a full-fledged study. But essentially what the students found was the following. If you're male and something like 5% of your friends on Facebook are self-describe as gay, then you're very likely to be gay. So you may not choose to release this information about yourself, but from this birds of a feather flock together phenomenon, it can be determined from the attributes of your friends. So hiding the sensitive attribute is a little dicey. Now, there's another problem with hiding the sensitive information, and that is that, in some sense, culturally aware algorithms can be more accurate than algorithms that, sorry. If you have a culturally aware algorithm, it can make very good use of this sensitive information to be more accurate. So in a typical example, and by the way, let me introduce some populations that I'm going to be using in the talk. We all like food, or most of us like food. Some people like to have their food flavored with the herb sage, and the rest prefer to have their food flavored with the herb thyme. And so my groups are going to be the thyme eaters and the sage eaters. And in this, generally, sage will be the minority group, but not everything will require that. Okay, so, and I'm going to be calling them S and T. So maybe you have a situation where hearing voices is a very common religious experience among the sage eaters, but among the thyme eaters, it's a diagnostic criterion for schizophrenia. This is a real medical example. So knowing whether or not one is a sage eater or a thyme eater permits better classification, more accurate classification. Okay. Now, as you all know, in machine learning, we train on historical data. Historical data is often biased, and so we can't just say train on the data because we'll imbibe the biases in the sort of mother's milk of training data. And this brings up a really important problem, which is that in general, there is no general source of ground truth for the things that we're trying to do. So we have to figure out how to sort of extract fairness when we possibly can, keeping this in mind. We can't just go to the training data. Now, who knows what this is a picture of? Okay, all right. This is a picture from the Sistine Chapel. It's Michelangelo's depiction of the Last Judgment. So we have Jesus in the middle, and on his left are the people who are being condemned to hell, and on the right are people who are going to go to heaven. So this is a binary classification situation. All right. You can have a ternary classification situation. So here we have some slides from brain tissue. Over on the left, this is cancer. On the right is healthy brain tissue. And in the middle, we have cancerous cells on the left, and these cells, they're not cancerous, but they're not normal either. They're affected by the tumor. So we might want a ternary or more complicated classification system for something like this. Here's another sort of classification problem. I'm calling this a dependent classification problem. So let's say that you're trying to hire people. Your job is not just to distinguish sort of the qualified from the unqualified, or even gradations among that. You have a more complicated problem. Maybe there are hundreds of qualified people and well-qualified people, but you only want to interview 10 of them because, after all, you have finite resources. So you want to sort of fairly select a cohort of people to interview. So that's a classification problem where you can't just classify each person individually as to whether they're good enough to interview. You have to somehow constrain it. Okay. And another kind of classification problem is scoring. Now, so here, this is a, what is this? This is something for evaluating arrested children to determine whether or not they should be eligible for detention or release, whether they should be detained or released. So it's a scoring system. You can see sorts of things like there are points for the various kinds of offenses that they committed this particular time. Then there are other sorts of points for their prior offense history. There are sort of negative points that come from mitigating factors. And these scores are then converted into a binary decision whether to release or to detain. And depending on the definition that you're using, fairness in scoring will or will not result in fairness in the decision. Okay. All right. So I still haven't defined anything. Now, we want to have a mathematically rigorous approach to algorithmic fairness. And historically, there's a way of trying to take these sort of big goals and translate them into a research program that should lead to some practicable outcome. So the first item in the basic paradigm is definitions. What are you trying to do? In our case, this is going to be, what do we mean by fair? So one way of doing this is that you can define fairness by thinking about what it is you're trying to prevent. So in a good cryptographic tradition, we imagine sort of an adversary, and the adversary is trying to force unfairness, and you want to defend against this. So what are the various behaviors or goals that the adversary may have that you want to defend against? So you define fairness. Then what you want to do, start with the definition, then you want to define, create algorithms, and you want that your algorithms will enforce whatever this thing is that you've defined. So once we have a definition of fairness, then we want to build a classification algorithm that will be fair according to that definition. And finally, we need a composition theorem. So think about the systems that you might use that classify people. Let's say you're determining whether they're appropriate for this ad or that ad, right? You don't just classify them once. You classify them over and over and over again for all sorts of different kinds of ads and many different times of day and all sorts of things like that. Similarly, if you're doing a privacy-preserving data analysis, nobody just wants one privacy-preserving statistic. They want a whole ton of statistics. Cryptography, you don't just see one message or one digital signature. You've got digital signatures on tons of different messages and encryptions of tons of different messages. So you need to prove some sort of theorem that talks about how these things combine in practice. And those are called composition theorems. So here what we would want is we would want to say that if you have a system made of fair pieces, then the system somehow is fair in toto. So this is a general paradigm that has been successful, particularly in cryptography and in privacy. So can we apply this to fairness? And the short answer is, I think we probably can, but it's way harder in my experience than in the other scenarios. Defining fairness is very, very difficult and very, very controversial. It's extremely, I don't believe it's going to be possible to come up with a single definition that will be, the technical community can come up with a single definition that the population as a whole would say, yes, that's it. All right? I don't think that's going to happen. Building algorithms, that's our bread and butter. Once we have definitions, there's been a lot of work already on building algorithms, some of it very recent and very exciting. So I'll talk a little bit about that. And composition turns out to be very tricky, and so we'll see a little bit about that as well. So let's talk about defining fairness. I said that we think about what it is an adversary is trying to do. So think about, for example, digital signature schemes. What do you want from a digital signature scheme? You know, you're all going to say the same thing right away. Nobody should be able to forge. Then you have to get into some details about all of the right quantifiers about what does it mean to say nobody should be able to forge, but forgeries are what you're trying to prevent, right? So what are we trying to prevent here? So one of our starting scenarios was actually in the context of advertising. So advertisers might be biased, and we want to build a platform that will mitigate the biases of the advertisers and be fair. So we literally sat around and said, okay, what are some of the kinds of things a really nasty, ill-intentioned advertiser might do? So redlining we talked about, and that's real. Redlining in loans was absolutely real. Housing loans, for example, in the United States. There's a fabulous book you should read by Richard Rothstein called The Color of Law, which talks about the effect of the US government in this biases. There's reverse tokenism. So let's say, for example, you turn me down for a loan. I say, oh, you turned me down because I have curly hair. And they point to Sergey and they say, obviously, he's way more qualified than you are. He has straight hair, and we turned him down too. And the thing is, they're using him as the example for all of the curly-haired people. So that's a reverse tokenism. And then there's what I'm going to call deliberately targeting the wrong subset of the sage eaters. And I'm going to actually postpone that explanation, that example for a slide or two. So we literally just sat down and wrote a whole bunch of negative things that we wanted to try to prevent. Is this a reasonable approach? Well, I don't know another one. And one of the advantages with this sort of approach is, let's say that you build a system that protects against all these things that we've listed. That's nice. And then somebody comes along and says, you missed one. You say, great. Now you redesigned your system to protect against the new one as well. In the meantime, you've been protecting against these first behaviors anyway. So something happened that was better than nothing. Okay. So when most people think about fairness the way I've introduced it, they'll immediately think in terms of groups. And in fact, the way I introduced it was suggestive of that. So what are group fairness properties are basically statistical requirements about the treatment of different groups. So statistical parity, which is also known as demographic parity, says that, let's say if we're just doing binary classification, positive and negative, it says that the demographics of the people with positive classification should be the same as the demographics of the general population. So the same proportions are being positively classified for sage eaters and time eaters as in the population as a whole, and also the same for the negative classifications. Now, this is nice. when is it really, really meaningful? As we'll see, it's mostly meaningful in the breach. If you see some incredible departure from statistical parity, that's a red flag. It doesn't mean that things have been unfair necessarily, but it certainly is a nice place to go looking to see, why did this happen? All right? So it can be meaningful in the breach, but it permits what we call, as I said, targeting the wrong subset of S. So I have a spa. It's a luxurious spa. And I really don't want those sage eaters at my spa. But I have to advertise to them in the same proportion as their proportion in the population as a whole. So what do? How do I be biased? I advertise to the members of S who can't afford to come to my spa. So I'm deliberately targeting the ones who can't come, and therefore I'm kind of ensuring that my spa isn't gaining new sage eaters. But among the time eaters, I advertise to the wealthy and they can come. Okay? So demographic parity, oops, it's not enough. And you have to look at it much more carefully. There's also this question of sort of the intersectional cases, which leads to what's colorfully called fairness gerrymandering. So we have our population, I've divided into the sage eaters and the time eaters, but there are also the tea drinkers and the coffee drinkers. And what we maybe really want is that if we look at the 4 different intersection categories, we should have proportional representation for each of these categories. Right? It would be very unfair if we only showed the ad to sage-eating coffee drinkers. So, I mean, you can fill in demographic groups for where you really clearly want this sort of intersectional parity. And statistical parity by itself does not protect against this kind of fairness gerrymandering. So, there's another issue, which is that, interesting, sorry. Another thing is, so statistical parity was one definition of fairness for groups. There are other definitions of fairness for groups. And then we have to face the fact that some group fairness properties are mutually incompatible. So how many of you know this story? No. So many of you do, but most of you don't. So I have a classifier. One thing that, so let's say that we are classifying people and we are predicting. So we're classifying as to whether we think you're going to do something, we think you're going to recidivate, versus we don't think you're going to recidivate. So importantly here, there's information that's going to be missing. Like the future hasn't happened yet. And whether someone released from jail recidivates may depend on many things that happen to them during their, their experiences. So one thing you might want, reasonably, is that you would have an equal false positive rates across your different demographic groups. Another might be that you would want an equal false negative rates across the different demographic groups. You might also want equal positive predictive value, which is among those who are predicted to recidivate, how many of them actually do. That's the positive predictive value. All right? And I chose these 3. These aren't my only 3, but these are very famous because it's known that no imperfect classifier can simultaneously ensure equal false positive rates across groups and equal false negative rates and equal positive predictive value unless the base rate is the same across groups. So unless the base rate of recidivating is the same across groups. And the reason, the reason for this, as Choldachova points out in her paper, is that these quantities are related by this equation. So we could write down for the sage eaters the false positive rate, the false negative rate, and the positive predictive value, and they would satisfy this equation where P would be the base rate among the sage eaters. We would then write down the same equation for the time meters. Now, requiring equal false positive rates across the two groups means that the blue terms would have to be the same in the two equations. So this term would have to be the same in the two equations. So then these blue guys have to be the same, and that blue term would have to be the same. And the only way this could happen is if the base rate p is the same in the two groups. Okay? Now, so no algorithm, when the future is unknown, so therefore classification would be imperfect, no algorithm can simultaneously ensure these three very natural desiderata unless the base rate is the same. And nobody cares how that algorithm is implemented. So if you believe in free choice or randomness, you get the same thing whether the algorithm is a machine or whether it's some other form. Okay? So it does not make sense to say, let's solve this problem by bringing a human into the loop. There's nobody you could bring into the loop that would address this problem. Okay. It's just the math. Okay. So as you can probably tell, I find group fairness notions dissatisfying for a number of reasons. I mean, I've shared some of these reasons with you. Now, this brings us to a very famous video. How many people have seen this? Not all. Great. I mean, not even half. So this is an experiment with capuchin monkeys. They're paired up. The monkey has to do a task, which is to hand you a rock, and then the monkey gets a reward. So let's see. Sorry.
What happens? So she gives a rock to us, that's the task. And we give her a piece of cucumber and she eats it. The other one needs to give a rock to us. And that's what she does. And she gets a grape. And she eats it. The other one sees that. She gives a rock to us now, gets again cucumber.
Okay. So that brings us to a notion that I prefer, which is individual fairness. And individual fairness says intuitively that for a given classification task, if two people are similar with respect to that classification task, then they should be treated similarly. Now, to make any sense out of this, we need the right notion of what it means to be similar or dissimilar. We need some kind of a distance notion. So a classic example is in credit scoring, where the difference in credit scoring literally gives you a metric for how dissimilar a pair of people are considered to be for creditworthiness. Okay. Now, and of course, again, I have to emphasize, this is a task-specific notion. So Sergey and I might be, in fact, comparably qualified for a loan, but for recommending hair products, we would be completely different. So we're similar for one purpose, but totally different for another purpose. So it's very important that when we talk about these metrics, they're task-specific. Now, thinking about credit scores, maybe people in general are sort of smushed uniformly from highly qualified to very unqualified. So that if in fact you sort of, so when you're trying to decide whether to give a loan based on whether somebody crosses a threshold, you may have two people who are very close, and you give one of them the loan and you deny it to the other one, right? And if the scores are in fact sort of densely packed along this line, then indeed that has to happen. So you sort of have to draw the line somewhere. That's the general worry. Then you would have very similar people who are being treated very dissimilarly. So what do the theoreticians say that you should do in this case? You randomize. So instead of deciding yes, definitely for you and definitely not for you, you assign to people a probability of getting the loan or a probability of getting an A, depending on their creditworthiness, and you arrange that if two people are very similar, then the probability distribution on outcomes that they see is very similar. Yes?
Two policemen were just fired for tossing a coin to decide whether to arrest someone for a speeding ticket. So they may have heard your lecture.
All I can say is that there are circumstances under which it might be the right thing to do. Police have huge amounts of discretion. And if they treat similar people similarly, maybe that's fine.
Well, but maybe instead of randomizing, one could just, instead of scale the loan, so instead of having a fixed amount that you lend, you could change the amount of loan till it, reaches zero for someone.
You could certainly do something like that. I would have to think through all of the ramifications, but there are cases where you must make a binary decision. So we're going to take this as our definition of fairness. So we have a set of outcomes. In this case, it's yes and no. That's O. This is the probability distributions on outcomes. So we want to find a classifier that maps individuals in our universe to probability distributions on outcomes with the following condition. For some appropriate measure of the difference of two probability distributions, for example, total variation distance, we want that the difference in these distributions will be bounded by the distance of these two individuals. So it's a Lipschitz constraint, the distance under the appropriate task-specific metric. Now, of course, this immediately says, where does the metric come from? How are you going to get your hands on the metric? And I don't have a great answer to that, but I also believe that if we actually had a classification system that people thought was fair, then we could extract from it a metric or, yes.
So how do we ensure that the metric is fair?
That's exactly what I just said. We don't know where to get our hands on the metric. So when we did this work initially, we said that at the very best, it was going to be society's best guess at the moment. And clearly what we would need, I'm now understanding more and more that these things are going to be handled by political processes, that there's no other way of getting these things other than combining stakeholders and measurements to get somewhere. But we don't have a straight mathematical answer for where we're going to get the metric. Yes?
There seems to be a tension between the who watches the watchman sort of argument, or the best person to decide if I'm going to offend you is you, not me. And in terms of individual fairness, it seems to be the case that if society will dictate that, we'll go back into group fairness. So for individual fairness, the toughest nut to crack is that the source of the metric is the subject to which the decision will be applied. As in the case of the monkey was the one that decided this is not fair.
Right.
So any hints as to how to, integrate other societal and individual fairness or separate them properly?
So I don't have a mathematical answer to that yet. And what I'm starting to engage in very heavily now is what is the right way of thinking about it politically. And I don't mean political correctness, I mean political theory and ethics. But it's an unknown. And, work on it, guys. It really makes sense. It's an important problem. Maybe ask me more about it at the end.
Are we right people to work on it? Are we right people to work on it?
So not by yourselves, unless you have a whole very broad education. But So, you know, inevitably, there's going to be legislation and regulation. We have to be sure that what gets legislated and regulated is not technically stupid, that it's not infeasible. And people will say, you know, I think there's a real risk of very bad law and regulation. So I think that the technologists have an important role to play in helping to steer away from that. Also, I think that technologists sort of hearing more about the concerns and the issues they have some of the tools needed to try to move those, act on those concerns. So we are sort of, but not by ourselves. You know. Yes?
How do we know that the metric is even computable? For example, right. if a brain is a universal Turing machine, then there can exist a computable function that maps from a universal Turing machine. You can execute any arbitrary Turing machine to a computable number, such as a metric.
So I'm hearing about 2/3 of your words, but you seem to be saying, how do we know that it's computable, in the sense of how do we know that information is available? How do we get our hands on the information which would give us the metric?
As in, if you suppose that a brain is a universal Turing machine,
okay,
and it can execute any arbitrary Turing machine, then no computable function can map from a universal Turing machine to a metric,
right?
Computable metric.
So I'm not sure what decision problem you're trying to work in here, like whether the brain stops on itself when it gets itself as a I don't know exactly. Maybe ask me after. I'm sorry. Okay, I'm going to go on. Let's talk a little bit about algorithms. So first, as I said, these are challenges with which we are familiar. So in the ad setting, we imagined a situation where we actually knew our universe of individuals, and we even gave the advertiser the opportunity to say for each individual and each potential outcome, how bad is it for this individual to be mapped to that outcome? So what's a loss that's associated by, incurred by mapping this individual to outcome O? And then with that, that's just something that we are adding optionally to allow the vendors to weigh in on things. And then we assembled the ingredients of the science fiction metric and the vendor's loss functions. We want to minimize the vendor's loss subject to the fairness conditions. So we're viewing the loss functions as soft constraints and the fairness conditions as hard constraints. And this is just a linear program. So in theory, this can be solved. And in fact, there's an interesting observation which is sort of evocative of those theorems about what you can't do when the base rates are unequal. If you solve the fairness linear program, you get a classifier that gives you statistical parity if and only if intuitively the distributions are the same. So the Earth mover distance between the uniform distribution on the sage eaters and the time eaters is 0. Now, recently, so that was something where we assumed that we knew the whole universe. Very recently, Rothblum and Yona have shown how to relax this a little bit to what they're calling probably approximate fairness, and then they get generalizability. We didn't generalize in our initial result. So that's a 2018 result. Now, I mentioned that there's been a lot of progress in recent years. So, for example, Hart, Price, and Shrubrow took equal false negative rate and equal false positive rate, and optionally also equal false positive rate as a fairness requirement, and they showed how to convert unfair predictors to fair predictors. Okay. Not for individual fairness. Their notion of fairness is these group fairness. And something that I think that you guys might appreciate is they did this all in post-processing. So as you know, if you're trying to get a product group to use one of your tools, it's much better if you don't have to interfere in their pipeline and you can stick something at the beginning or the end. So that's something they did. Then in other work, Joseph Kearns, Morgenstern, and Roth looked at a different problem. They were looking at a bandit setting. So you have basically one arm for each demographic group. So in our example, there would be 2 groups, but it could be more general. And they're worried about the fact that you may have a lack of training data for your minority group. So for the sage eaters, you don't have a lot of training data. And what they require is that at each round, let's say, think about this in terms of loan. At each round, one person from each demographic group comes and you have to choose one to give a loan to, or at most one to give a loan to. And maybe what you'll do is you'll actually choose a probability distribution and you'll then choose somebody from that distribution. And the requirement is that a worse applicant will never be favored in terms of these probabilities over a better one despite uncertainty. So they study how to minimize the regret and learn a fair policy. So they look at the difference between the regret that you get when you enforce this kind of fairness condition, which basically costs you while you were learning about the minority group. Once you know the minority group well, you can predict with confidence, but when you don't, you can't. So they show that there's a gap, that it's more expensive. You have higher regret when you're learning a fair policy versus regret when fairness is not a concern. There was a question?
Yeah, so what is the fairness definition used here?
They're using individual fairness at each round among the people who have shown up at that round.
So you're saying the probability that you choose each individual shouldn't differ.
Right, shouldn't be. Right. Mm-hmm. Actually, no, sorry, they're doing something a little bit more coarse. Just that a worse applicant is not favored over a better applicant.
Oh, that itself is.
Yeah, sorry, yeah, I misremembered. That's the run for this paper. Yeah, okay. So that was 2016. 2017 was a really interesting year. So 2 independent groups of researchers started looking at some of these things, similar questions. So now we're getting into the intersectional case that I mentioned before. So imagine that you have, for the first paper, this is where the gerrymandering nomenclature came from. Imagine that you have a couple of sensitive bits for now. Let's say K sensitive bits. So sage versus thyme and coffee versus tea and a couple of other sensitive bits. This gives you 2 to the K subsets. Suppose all of those subsets are still large. They're not tiny relative to the population as a whole. Then this first, so this is sort of large intersections of large sets, all right? So they're handling the intersectional, or they're studying the intersectional case, and they want to learn a classifier that will essentially ensure, well, they looked at a few different notions, statistical parity and equalizing the false positive or false negative rates across these intersectional sets. And so I described it as being defined by, say, K bits, all of the subsets of those K bits. But you could have other ways of describing your collection of sets, like a set of all the sets that can be described by small circuits. So as long as the set is large, these sets are large enough, they want to try to guarantee these notions of fairness across the groups. They also showed that the general problem of what they call fairness auditing is hard. So I give you a classifier and these descriptions, perhaps implicit, of these groups. How do you determine whether there is a group to whom you're being unfair? One of these intersectional things to whom you're being unfair. And they showed hardness by reduction from agnostic learning. So the reason they can have an algorithm as well as these negative results is, as you all know, machine learning often does interesting things, even when, in theory, they're hard. Very similar questions were looked at by Aber Johnson, Kim Reingold, and Roth. Wait, I made a mistake. This is Roth-Blum. The other one is Roth, this is Roth-Blum. And they studied calibration. So suppose my predictor is now giving a score. And so I'm going to rate people some number between 0 and 1. Think about this as my prediction about your probability of recidivating, for example. So the system is calibrated if among those that are rated V, the fraction who truly will end up with a positive label is close to V. So in other words, it's requiring correctness on average for those rated V for all V. So they got results that were very similar, but they're using this kind of notion of correctness as fairness through the calibration version. If you're familiar with the Kleinberg-Mullainathan and Raghavan result, this is the kind of calibration notion there, or it's related to their calibration notion. And they argue that this makes more sense than these other group fairness notions. But other than that, they get very similar results. So for every set defined by a circuit in a predetermined set C, they get this approximate calibration simultaneously. And subsequent work by Michael Kim and James Zoe has shown that this has been, they've used this to improve some medical predictors. They've gotten some nice results. Okay. And then, how long is my talk?
We have a soft stop around 4 usually, but we have the room much longer.
Okay, I'll talk for just a little more then. Okay. So the next batch of results deals with algorithmic work that tries to bridge the gap between group fairness and individual fairness by assuming that we have some sort of oracle that tells us we can ask about certain collections of edges and say, what are the distances on these edges? And then it leverages that to do powerful things without requiring you to ask about all pairs. In the deep learning community, there's a whole different approach, which is adversarial learning, or learning of fair representations, and adversarial version of that. So this is a group fairness notion. Oh, shoot. Sorry. All right. I'm going to skip this slide. Okay. So the general idea here is we start with instances in some set X. And we're going to learn a new representation for people that in some sense retains as much information as possible while suppressing some key attributes, such as whether somebody is or is not a member, a sage eater, whether they're a sage eater or a time eater. And they're using GANs. And so we've got an adversary that is trying to distinguish, given a Z, whether it came from the sage eater X or a time eater X. And the key point in this, the intuition, is the predictor is going to operate on the representation Z. If the predictor is not so powerful as the adversary, who is trying to distinguish sage eaters from time eaters, and who has trained the encoder to make that representation not yield distinguishability. If the predictor is no more powerful than A, then in some sense, its predictions can't be biased. This is really, really intriguing. It is a group notion of fairness, and I would love to see individual fairness worked in here, but this is another very interesting direction of research. So in the last 5 minutes, I'm going to talk about composition, because this is really interesting and this is new. So our intuition is, if we have a system in which we have a bunch of individually fair pieces, then when we look at the system that's made of these as a whole, it's still at least relatively fair. And the answer is, it's complicated. So here's a very simple example. Suppose, let's make the example really simple. You're looking at the New York Times website, and there is a single slot for a banner ad at the top of the page. Okay. that's going to be our scenario. And well, as you know, there's an auction run for your attention. Advertisers are competing to get that slot. So let's look at the case where we have two kinds of advertisers. One is advertising tech jobs, and the other one is advertising a grocery delivery service. So the tech jobs advertiser and the grocery delivery service advertiser are competing for your attention. And we want that, ideally, if our classifier for determining who is a good bet for the tech jobs ad is fair, and if our classifier for determining who's a good bet for the grocery ad is fair, then somehow the system will be fair as a whole. But we want to require that in this complex system, it's still the case that people who are similarly qualified for tech jobs should be similarly likely to see tech job ads, and same thing for groceries. So suppose that the grocery advertiser routinely outbids the tech jobs advertiser. It's an auction. The outbidder wins. So we can even think of it as just the outbidder goes first. The grocery advertiser is going first, or it's bidding more. All right? And so the tech company is now essentially being reduced to the leftovers, the ones who weren't grabbed by the groceries advertiser. This is true, again, whether it's done temporally, first one then the other, or whether it's just done by the money bids. So, this is a major problem. It says that no matter how qualified you are for a tech jobs ad, if you're very qualified for groceries, you're not going to see the tech jobs ads. Now, who is qualified for the grocery service, the grocery delivery service? New parents. Advertisers drool over the things they can start advertising to new parents. And those tend not to be the tech jobs advertisers. And in fact, the tech jobs advertisers, you might say, shouldn't touch the parenthood bit with a 10-foot pole. So even if they're really appropriately not looking at parenthood status, you would think it was appropriate not to be looking at parenthood status and determining who should see the ad. Their competitors for your attention are looking at that, and that's affecting what happens under the tech jobs advertiser. Okay, and there are versions of this particular problem both for individual fairness and for group fairness. So this problem doesn't go away. No time for these things. There is a way out here, though, which I will mention, which is we could fix a probability distribution on the advertising tasks, any probability distribution we want. Then we pick a task according to that distribution, and then we run the classifier just for the chosen task. And the proof that this gives us fairness is, individual fairness, is very, very simple. But it leaves money on the table, because there are some people for whom we are just not going to be showing ads. So that raises a number of very interesting economics questions for those who are interested in the intersection of algorithms and economics. And because of time, I will skip the rest. Wow. Final comments. First of all, interpretability and causality. There are big literatures on interpretability and causality for fairness. Why is this slide left blank? First of all, I have tried very hard to make headway with interpretability, and I have failed. I don't understand what's being asked and how it can be achieved. There's a very interesting article called The Mythos of Interpretability by Zachary Lipton, and he explains, he sort of catalogs, these are some things that people could want, and here are some of the issues. It's very, very thoughtful. And I'm not done thinking about this, but I'm stumped on this one. As far as causality, it's problematic for a number of reasons that I can see. So first of all, if you're using, say, Pearl's theory of causal reasoning, you need a generative model. Now, maybe you're familiar with the saying that all models are wrong, but some models are useful. So if your definition of fairness ties the classifier to the model, and is, you need those two together to determine if something is fair, and your model is wrong, you may very well come up with the wrong conclusion. So that's a glimpse into what some of the difficulties I've encountered with causality are. And there, yeah, okay. Another brief comment is we've talked about the metric. We've talked about the issues of where do you get the metric from. Even if we sort of, there's still problems. So here, suppose we have a news organization, Nice News, and your news organization has an environment. There's randomness in the environment. You have an individual X, there's randomness in X. But you can sort of talk about, although you can't get your hands on, the probability that an individual X, this individual X, will succeed at Nice News. It's well defined once you specify the coins for this randomness and the coins for this randomness. Again, you can't get your hands on it, but at least it makes sense mathematically. Now, what you might require is that if two people are similar, meaning they have similar probabilities now in success, and success can be very crisply defined, like you stay in the company for at least 3 years and you have at least one promotion during that time, okay? So if you might say that if you have two individuals who are sort of equally likely to succeed, then they should have very similar probabilities of being hired, okay? So that seems to make some sense. So the metric then is capturing the probability of success. But what happens if this is not nice news, but it's nasty news, which has a history of being very hostile to sage eaters? So sage eaters can't succeed no matter how talented they are, or they'll have a real uphill struggle. So should the metric in fact be capturing whether people are equally likely to succeed? Should it be capturing whether they're equally talented? What's the right thing to do here? It's not clear. So final remarks, truth is elusive. It's not remedied. This problem is not remedied by having a computer. And if you, and I really, as I've argued, I really believe that metrics are really at the heart of everything, even if it may take us a long time to find them. But we advocate always sunshine for the metric. The metric should not be kept secret. It has to be open for debate and discussion and refinement. Computers are not necessarily worse than humans. They may be more accurate, especially on the easy cases. They may be more easily tested. They don't get tired when you keep throwing examples at them to see what they have to do. And that's it. Thank you. Sure. Go ahead. Sorry, I'm one behind and then you.
Really interesting talk. I'm sure you've thought about this, and it might even been what you were mentioning on sort of the previous slide here. I'm curious to hear what you think. So, in considering the individual fairness, if we're looking at the sage eaters and the time eaters always teach their kids to eat time, and there is this terrible, sagebrush infection or something, right? That infected all the sage and made anyone who eats sage get very ill. Right. And so this sort of via this terrible historical injustice, right? All the sage eaters, they just did way less good at virtually everything because they were so focused on handling this illness.
Right.
So it just so happens, via this sort of historical coincidence, the sage eaters are almost never like a similarly situated individual to be able to compete with the time eaters. It seems like on that individual fairness metric, we would just say, okay, no problem. Right. And if we're deciding jobs, then it's the time eaters that get all of them whereas we're not considering that sort of group aspect. And I think there's some analogs we could make, in sort of society for these kind of historical injustices.
So that's, of course, an excellent point. And in the paper, we described what we called fair affirmative action, which is a method for dealing with this, where we break certain of the Lipschitz constraints for exactly this reason. But it's a principled approach to this sort of thing. And I should mention that it's not so unlike what the state of California does and the state of Texas does with respect to college, that if you're in the top 10% of your class, then you're eligible you're admitted to one of the state, in California it's one of the UCs, and in Texas it's one of the state colleges, I guess. And the point is that schools in different neighborhoods may have very, very different performances on tests and so on and so forth, but it's the same basic idea. So we add a bit to that. It's not quite as coarse as taking the top 10%. There's a very interesting work by John Romer at Yale, who is very concerned with theories of distributive justice, and he thinks a lot about education. He thinks that you must invest and invest and invest in children in order to compensate for differences of situation, and that sort of as you go through the schooling process, you do less and less of this compensating because the children, having been given a good foundation, are more, theoretically, I guess, more responsible for how they make use of what they have. But in particular, I remember he said the following: in the context of college admissions, stratify the students according to the education level of the mother. And within each stratum, look at the cumulative distribution function describing how many hours a week the students spend on homework, and view people in the various percentiles in that CDF from the different strata as being comparable. And one of the points he makes, which I found extremely compelling, is that if you're brought up in a home where nobody is educated, then you may not even think that it's possible to spend 10 or 15 hours a week on homework. It just doesn't cross your mind to do it, or you might be working and unable to do it. So I think that these sorts of insights from the social scientists are very important, and what we are doing is, in some sense, analogous to that. Yeah, it's a very good point. Yeah. Yes?
So that whole conversation is basically related to this nasty news, choosing your metric thing, right? And it kind of comes down to questions of what you want to condition on and mediating variables and stuff. And basically the rest of the talk didn't address those types of issues, right? Like how to choose the metric fairly. Mm-hmm. Is there any work that uses graphical models or other ideas from causal inference to kind of, because we have this intuitive idea of, oh, well, we should condition on these things. We want to make a fair metric, but we definitely don't want to condition on these other things. Right. Is there any work that tries to formalize that?
There is work. There are so especially so yes, there's work. It's very interesting, and if you're interested, I can point you to a bunch of papers. The one difficulty with some of this work is that you can have the same sort of observable distribution on data that's consistent with very different causal models. And so that just causes problems.
Fitting causal models is just really hard.
Yeah. So I don't know what to say about that yet. I was really excited when I sort of saw there was a counterfactual fairness paper. I thought, yes, this is it. But then we found two different models that gave rise to the same distribution, and the classifier, and the thing was fair under one and not under the other. So what do you do? You know. Yes. Yes.
So suppose I want to get a chess team for my school.
You want to get what?
I want to select the chess team of 3 people to represent my school at some competition.
Right.
And so what I probably do is I try and measure how good the people are and take the best 3 by measurement. And it seems like by your definition of individual fairness, the more accurately I can measure people, the less randomness there is, and the less fair it is.
You introduced the randomness.
I mean, there's some random.
No, I'm saying that the algorithm introduces the randomness.
I mean, if you just take like what people typically do, they're not going to introduce randomness out of the fact that there will be randomness, and because some people win, some people lose, there's randomness in how well you can measure people's skill.
Mm-hmm.
And so it seems like, by your definition, the more accurately we can measure people's skill, the less randomness there is, the less fair the selection process is.
So if you're saying that you can get very, very, very...
Like maybe put another way. Why is a completely random process more fair than a meritocratic one?
Right. Okay, so this is the kind of problem that shows up in fairness all the time. I mean, you've sort of, from this particular example, you've sort of hit the nail on the head. So in the definition of individual fairness, I mean, buried in there is the idea that if you simply flipped coins all the time, that would be fair. If all you did was decide whether someone could be on the chess team by flipping a coin, certainly similar people would be treated similarly. What we're not ensuring is that dissimilar people are treated dissimilarly. So this is where we want to throw in the, well, minimize the loss subject to the fairness conditions, and we want to incorporate some notion of loss in the decision process. So we want to stay fair, but we also want to maximize utility.
I think it's not fair to be... It's not that you're like, a fairness constraint is to be random.
So I know what you're saying, and you can probably come up with even better examples of where randomness is unfair, or we're treating everybody the same way is unfair. And often it's possible to kind of reframe the problem so that you're pushing those concerned into the objective function rather than the fairness. Yeah. By the way, we thought that we were so original with similar treated similarly, but of course Aristotle says the same thing, and Aristotle says dissimilar should be treated dissimilarly. Since we were thinking initially about advertising, and I was thinking about how when you look at a physical newspaper, you know, everybody gets the same ads. It has nothing to, there's no targeting. So that seems pretty fair. And in terms of like exposing young people to ads for luxury goods, does that help form aspirations or not? Should you be saying that poor people should not see, poor children shouldn't see nice things or pictures of nice things? So there are people who work on these kinds of questions from the psychological and sociological point of view, and they think that, yeah, that ads are very tied in with the formulation of the self, and that having a real difference in what people see is harmful. So, I don't know. Yes?
So, when hearing the conversation about individual fairness metrics, I was thinking about drug treatment effects, and where you're doing these randomized control assignments, and you're thinking about, here is a population, let me find someone from this other population that matches well, see the treatment effect when different treatments are assigned. Right? And really, I can imagine a dual sort of problem here, where you really want the classifier to behave like a placebo for these matched individuals rather than as a drug with some treatment effect. And that actually boils down not to the individual fairness where you're assigning this metric on every pair of individuals in the population, but only like across groups.
Right.
And then you do allow meritocracy within a group, but you want placebo-ness across groups.
So this is really interesting, and I don't know. So I mentioned that in the in the causality literature, there's been work sort of in the Pearl model, but in the Rubin model, I don't know of any. They may be there, but I don't know of any, and I want to look at that. So I think this is definitely worth thinking through. So very good question. Yeah. Wait. So yeah.
I was wondering about something. So, because the title is about this going towards a theory of modeling fairness, I was thinking, have people tried to turn it around and say that we are going to accept that things are going to be unfair, and we want to actually quantify the degree of how unfair things are? In other words, instead of treating them as fairness constraints, trying to put them into maybe equivalence classes of, like the way people study like program classes would say P and P. Are there thoughts, and do you have any thoughts in that direction?
I only know of one theoretical result along those lines, which when I was talking about when individual fairness implies statistical parity, in fact, there's a sort of tighter characterization of how unfair it is in terms of the earth mover distance between groups. But I don't know of, I guess some of the very recent works do look at what happens if you relax things a little bit, like that probably approximately fair notion. So you're saying, okay, we'll introduce a little bit of slack, what can we get from it? So there is some of that. But I don't know of sort of wholesale saying, okay, well, we're just going to treat these people this way, and I don't know.
I was wondering, in differential privacy, there's this trade-off of as epsilon parameter. You said you get you're somewhere, you lie somewhere on that curve.
Right.
You give up privacy to get more accuracy. If you
so if you think about it, the definition of fairness is very similar in flavor to the definition of differential privacy, but it doesn't behave the same way under composition. And there is one result also about using a particular algorithm from differential privacy to ensure fairness, where again where the trade-off that you talk about would perhaps be relevant. Anyone else? Yes.
I have a question about the practice. So this problem is complicated. You've given a very beautiful summary of the related work and talking about how it's going to take a long time to reach maybe consensus, maybe not, but some legislation on this. At the same time, computers are not necessarily worse than humans, and people are trying to put machine learned models into the world in different domains.
Right.
What is your prescription about what needs to be done right now? Do we stop and wait until we really understand these things better? Do we apply some reasonable approach because something is better than nothing? What is kind of the practitioner's guide of what needs to be done?
So I feel wildly unqualified to answer that question, but I'll try anyway. So even if I thought, and I don't, but even if I thought it was appropriate to wait, that's a non-starter in the business world. Facebook is not going to stop. You just cannot stop industry where it is, I think. The political forces are way too strong. Now, what you can do, of course, is start creating test sets where there are at least the people who create the sets believe they know what the outcomes should be. And so for example, algorithmic assistance in bail determination, right? It's happening in many states. I can't remember the number. I'm sure it's at least 12, but I can't remember why that number is in my head. So it's happening in a lot of states. So one thing that we would want, I don't know how useful it is to see the code because, code can be hard to understand, but certainly you would want that somehow appropriate people and organizations should be able to throw test cases at the algorithm and see what it does. So I would say really intensive monitoring with the best golden sets you can come up with, and lots of people doing it. I think that's where we are for now. Yeah, okay. Because monitoring you can do. So, yeah.
So if you just do what people are doing and try and maximize your accuracy and release these algorithms in the wild, are there any instances where it's clear that it went bad?
Where it's clear that the algorithm has gone bad?
Yes. Oh yeah, controversially.
Lots of cases.
Like what?
Speed bump. Is that what it was called? Street bump? I forget. So pothole detectors that will report to the municipality about potholes, but this was an app on an iPhone, and so the only areas that got the reports of the potholes were the wealthy areas.
But it seems like that's an issue where it's not as accurate as you would like, right? Like so the question is, if
it was certainly an unfair impact.
Accurate, then okay, that's like a problem you'd like to fix. That like the people making that app would like it to be more accurate, and that's what they're trying to do. They're not
no, I'm sorry, I don't understand. If the app isn't being brought over the right potholes, if it's not penetrating into the poor areas of town, it's just not giving you the information you want. The system as a whole is unfair. So you're saying, is there a classification algorithm?
But basically that's so it's like there's like the minority group in which it has less data, and so it's less accurate. It's roughly what that is.
It had. I mean, I'm not sure that it was inaccurate where it was. It just wasn't coverage. There was lack of coverage. Okay.
As maybe I don't understand, but like you're talking.
Okay.
So like the accuracy.
You want to go ahead and want to provide an example?
Yeah. So compass. So if you define fairness by.
Wait. So you're going to start with compass.
Right.
Now the problem with compass is that they were test fair.
Right, for those criteria, but they weren't for positive and false negative rates.
Yes, but they were test fair, and it's impossible to simultaneously be test fair and have equal false positive rate and have equal false negative rate. So
I'm looking for one where it's clear that it's unfair by like if you like talk to a random person on the street, then it's very clear that it's unfair.
So
college admissions? College admissions and wealth?
College admissions and wealth is probably a really good example.
So affirmative action is controversial, right?
This is part of the issue. Remember, I began the talk by saying that there's consensus, at least, there's more consensus on privacy than there is in fairness. So is affirmative action fair? What do you think? There would be a range of opinions here as to whether it's fair or not. Have there been examples historically that use classification algorithms that were very biased? Yes, the answer is yes.
So when we talk about fairness in classification, it seems like some classification problems are less important than others. For example, if you're trying to decide what ad to show someone, that's a classification problem. But if a car is trying to decide which person to kill, that's also a classification problem.
So here's what I think we should do about the cars. Is this your question or not?
Well, I mean, what were you going to say?
Oh, thank you. All right. So for a while I thought, oh my God, we can't do anything until we figure out what's right to do in all situations. And then thinking about the cars, I thought, well, suppose you have an algorithm that what you do is you learn what do average people do. Maybe you use the moral machine for this. Maybe you have some other way of figuring out statistically, but you learn what sort of a random person would do. And then your car driving algorithm should do the following. When it gets into one of these really touchy situations, it should do what a random person does, and the rest of the time it should just do its automated driving. So this would be much better than humans, because in all the usual situations it'll be more accurate, and in the really wacky ones it'll be no worse than humans. So altogether it's better.
When you say, oh, what a random person would do, what does that really mean? Do you mean like, I mean, I think one way that this might, like one intuition is that everyone is equal, so there's no way.
So what a random person would do. So there's some probability distribution, and you just draw from that distribution and you do what that person does.
Is that shifting down the problem though? Like when do you switch mode? Is it really just shifting the decision there?
So I was thinking that it would not be difficult to know when to switch modes. That most of the time it was totally clear what to do, and then sometimes there was a moral question, and then you go to your database of what would people do, and you consult that. So, yeah.
That also seems like it would just reinforce societal biases if you're sampling from a biased sample, as people are biased. Even if you pick a random, that's going to be a biased decision.
Okay.
I have a question about, say, sorry.
Last question. Go ahead.
Okay. I have a question about the data part. So it seems like a lot of this comes from just, that the data set that this kind of problems, that fairness problems are frequently biased, like recidivism data sets. Black people tend to be arrested at higher rates, even compared to white people. So the base rate already starts off being biased in that sense. So maybe like an income example, for instance, like maybe you don't see so many women CEOs, and therefore if you are trying to do a model where you're predicting pay, they tend to be fewer highly paid women historically, so you don't even have that data in the first place.
Right.
So it seems to me that there should be some, some kind of work, like just working in the data space, trying to maybe hallucinate what fair training data would look like. Something.
There are efforts that involve what I would call massaging training data, exactly as you're suggesting. I don't know how to put them on a sort of firm theoretical foundation, but people have thought about those sorts of things. Yes. As you say, they sort of you could hallucinate some data to change your training set. I don't know a lot of work on doing that and how you would do it, but I guess, now that you mention it, statisticians do this sort of thing all the time when they weight their samples. So something maybe could be doable, but then you have to decide, how are you going to do that weighting?
So one last comment is like the Rubin counterfactual fairness approach.
What was it?
Rubin style counterfactual fairness. So not Pearl style, but Rubin style. You would be trying to weigh up the women's CEO because she's very rare in your sample compared to a man CEO. So when you actually train on it, you weigh up the woman CEO a little bit more, and the propensity scores is to find that weight.
Yeah. So as I said, I think it's a really good idea to try to pursue that direction and see what it gives.
There's an ICML paper about that.
Cool, awesome, yeah.
Okay, good. All right.
Thank you
all very much.